My name is Undertaker Jones, and I will be covering Chapter 13, The Death of Stars. Quite fascinating, actually. The Sun is the brightest star. Now, the more massive a star, the shorter it stays on the main sequence. The most massive stars may only be there for a few million years. A few types of stars explode violently at the end of their lives, but our Sun will expire in a less sensational manner, sadly. That is also why we usually see stars twinkling at night. When the Sun dies, it will follow the same path as other single lightweight stars. Lightweight stars are born up to about 10 and as low as 8 times the mass of the Sun. Both the Sun and lightweight stars will go through a planetary nebula. Massive stars greater than about 8 or 10 times the 8 or 10 times the Sun's mass are called heavyweight stars. The most massive stars go through spectacular stages, and if they have enough life left in their final stage of life, they can become a black hole. Now, if you're wondering, what is a lightweight star? Well, if you see right here on the left, an example of a lightweight star is the Cat's Eye Nebula. Just like the Sun, it is late in its evolution, with all planetary nebula radiation coming from the hot central star provides the energy for the nebula to shine. Now, if you're wondering, well then, what's on the right? What's a red giant? Well, my dear friends, red giants are a luminous star that we can see from a long distance. An example of this is Aldebaran in Taurus, as you can see with the arrow to what it's pointing to. When the star's solar surface becomes cool, it will appear very reddish, becoming what is known as, you guessed it, a red giant. Red giants are so bright that we can see them at quite a distance. Now, planetary nebulae, or nebula. During the second period of a star growing in its red giant phase, hence why we talked about it, its helium shell becomes unstable and undergoes periodic pulses. These clear bursts of energy start off as a slow wind, followed by a fast wind, and finally a super wind, all accelerated by an exposed stellar core. The loose outer layers continue to move away until they finally leave the star, creating the glowing gas that is energized by a hot central star, creating a planetary nebula. Nebulae. The most well-known version of this is the Ring Nebula in the constellation Lyra. Using a special telescope, only photographs can reveal the vivid colors that show up, as you can see on the left here, that are very similar to Uranus. Although, given the name, they are not related to any of the planets. Pardon me, just fixing my notes here. Now, what is a white dwarf star? A white dwarf is the final stage of a star's evolution. It comes from the friction of electrons becoming too close together, making them degenerate and end up differing in their energy levels. This results in a type of star called, as you see, a white dwarf. The main sequence stage is the star's most active part of their lifetime. All subsequent stages are much shorter except for the white dwarf stage. But white dwarfs do not create nuclear energy. They use their life savings of stored energy. They are not a part of the active phases of their life. Now, Rush lobe, I am sorry if I butchered that, is the region of space around a star in the binary system within which orbiting material is gravitationally bound to the star. When it transfers its material to 12 white dwarf companions, it forms a accretion disk, eventually producing a dwarf nova outburst. Now, a nova is the result of an already made white dwarf, and the companion donor fills its Reich lobe, making a nova. Once again, I apologize if I'm butchering that. A nova's old star that becomes more bright by a factor of times 100 to highest is 1,000,000. Now, supernovas. Heavyweight stars slowly give off faint planetary nebulae, ending their lives as white dwarfs, some of them joining bigger stars and going off with a huge explosion dash as a supernova. Now, a core collapsing supernova is, for these stars, have become big enough and also cooled down enough that we call it a red supergiant. An example of this is the Betelgeuse star. I'm sorry, I didn't mean to push that. In the 1920s, it was realized that some of the novae, which were new stars, had been seen in other galaxies because they were much more brighter than the ordinary novae seen in our own Milky Way galaxy. Without supernovas and the debris of old stars, especially the Sun and the Solar System, would not be where they are today. The elements that were thrown out by collapsing supernovae and white dwarf supernovae what made that happen. Supernovae are the only source of most heavy elements, especially those past iron on the periodic table of the elements. Best of their sped through space, they later are made into stars and planets. We humans are here today because of the natural process of recycling of a star's life. Cosmic rays. They honestly aren't even rays, which is funny considering their name. They are nuclei atoms moving at a very fast rate. Cosmic rays provide about 1/5 of the radiation environment coming from Earth's surface. Almost all of the cosmic rays us humans are exposed to come from that. Because these rays are charged particles, we mostly give the portions, and also some nuclei of atoms, heavier than hydrogen and fewer than electrons. The magnetic field of our Earth bends them naturally. Now, coming to a soon close, pulsars, or pulsars to some others. A pulsar is a magnetized spinning neutron star that gives off electromagnetic radiation. We can only see them when pointing towards Earth, when they are pointing towards Earth. My apologies. Now, a lighthouse model is the best way of explaining what a pulsar is, involving the spinning of a star that gives off a focused beam of radiation. The reason we are talking about pulsars is because they are part of the supernova and the creation of the Crab nebulae. When looking at the Crab nebulae, scientists found out that after several months of the first pulsar, they discovered strong bursts of radio energy coming from this nebula. They thought that the white dwarfs might be the cause of this. They ended up actually being checked off the list of explanations because of how fast the bursts were going. The energy given off from the pulsar slowed down and was the exact amount needed to keep the Crab nebula lit up. Now, wrapping up here, another reason a pulsar is important is because it also helped astronomers and scientists discover a planet. In 1991, they discovered that the arrival of the time of Pulsar's radio varied slightly and indicated that something was orbiting the pulsar, making it go back and forth a little bit. The astronomical units of the planets that these pulsars were giving off are 0.19, 0.36, and 0.47 from the pulsar, which is the same distance when compared from Mercury to the Sun. Last but not least, we will be talking about X-ray binaries. They are a class of stars that are very bright and they produce matter that falls off their component onto another component, creating a neutron star. X-ray telescopes in orbit detect them in pulses if there is a rotating beam of emission. As the final days of the star come to an end, the only possibility left for them is to become a black hole. That, though, is a whole other chapter within itself, and I will not be covering that. Thank you for listening and learning about the life and death of stars. Have a good day or night.